Now that we know the arc-trig functions, let's apply it to our favorite application, finding the equation of a tangent line yet again. So remember that the equation of a tangent line will be equal to y minus y1 equals the slope of the tangent times x minus x1. That's how that works. Okay, so we need to find several things. We were given an x1. It's right here. And that part was given. But we're going to need to find a y1 and a slope of a tangent, and we all know that the slope of a tangent means we're going to have to find a derivative. So we've got our work cut out for us. So let's start by finding y1. Why not? So let me do that right here. So step 1, let's find y1 since it was not given. If you're given a point, then you can use it. But the problem is that there was no point given on this one. So we just gave an x value, not a coordinates. So we're going to find the y1 coordinate. Now the way to do that is to say, all right, well, y is equal to the arc secant of e to the x. So e to the natural log of 2. Now at this point, it pays to remember that e and natural log, the Euler number, right, exponentiation, e to the x and natural log of x are inverses of each other. What does that mean? Well, it means that they will undo each other and just leave us the number 2. So, which hopefully you learned in algebra somewhere along the way, but that's all right if you forgot it. But they're inverses of each other. So that's going to mean we're taking the arc secant of 2. All right, so that means I need the arc secant of 2. So I need an angle in the unit circle that would give me a secant of 2. So let me just write this down real quick. That means that I'm looking, remember what arc functions do. Arc functions take a ratio and give back an angle. Right? So I'm looking for an angle. So find an angle such that the secant of that angle would be equal to 2. But remember, secant is 1 over the cosine. So that means 1 over the cosine of that angle is equal to 2. And if I think about that for a second, I realize, oh, I can multiply both sides by cosine, divide by 2, and that means that the cosine of that angle is equal to 1/2, because secant and cosine are multiplicative inverses of each other. But that sets off little bells in my head, because I know an angle in quadrant 1 that has a cosine value of 1/2, namely this angle right here. It's over 1/2 up the square root of 3 over 2 is the point on the unit circle, and that's the point associated with the angle right here of pi over 3. Okay, so that means that the angle would be pi over 3. Here, pi over 3. So that means that this is pi over 3. All right, so just reiterate, when you're looking for an arc secant function or an arc any function, they take a ratio, like 2, and you have to find the angle that would give you that ratio. So you're looking for an angle in your unit circle, but only in your restricted domain. So you'll notice I didn't go grab the one that's in quadrant 4, even though there is one. And that's because arc secant is restricted to domain, or to quadrants 1 and 2. So I'm only going to look in quadrants 1 and 2 to find an angle that would have a secant of 2. But if it's secants 2, that means its cosine's 1/2, because these two, secant and cosine, are multiplicative inverses of each other. That's one of the trigonometric identities. And then the angle that has a cosine of 1/2 in quadrants 1 and 2, which I should highlight because those are the only quadrants I'm allowed to look in, right, for arc secant. So in those two quadrants, then the angle that would have that is pi over 3. And I'm just going to bring this up real quickly so you can see what I'm talking about. So if you look at arc secant right here, right, arc secant has a range, see right there, from 0 to pi. We're only allowed to look in those two quadrants that I highlighted, and that's it. All right, so step 1 is done. Hooray. All right, step 2. Well, if I'm going to find the slope at some point, I mean, I've got my x1, I've got my y1. Oops, let me just label this real quick. This is y1. That's what we found right here, y1. Right? Hooray. And I've got my x1 right here. Now I need my slope of my tangent. But to do that, I'm going to have to find the derivative. So step 2 is going to be find dy dx. I don't want to bite off more than I can chew, so I'm not going to say find the slope. I'm going to find the derivative, and then step 3 will be to find the slope. Okay, so dy dx, let's see, my function was y equals arcsecant of e to the x. So if I look at that, I can think, well, this e to the x is my u. So when I look at my rules of derivatives, the derivative of arcsecant of u is 1 over the absolute value of u, the square root of u squared minus 1 times u prime. Okay, so that means that dy dx, if I take the derivative of both sides here, d over dx of all of this, I'll get dy dx equals, okay, according to that rule, it'll be u prime, which is e to the x, because the derivative of e to the x is e to the x, over the absolute value of u, that's e to the absolute value of e to the x, square root u squared, so e to the x squared, take away 1. Now there's a little trick to doing this, and you can't always do this, but you can here. E to the x divided by e to the x. If they're opposite signs, then that would make negative 1. And if they're the same sign, then that would be positive 1. But the thing of e to the x is e to the x, imagine the graph, it's exponential growth. It's always positive. And since it's always positive, that means that we can legitimately just scratch that off and say positive 1. Because they're the same thing, but they have the same sign. Now, if e to the x was negative, then it would be negative 1, because they're the same, but then opposite signs, because this is always positive and that would be always negative. Now, if it switches signs, then you can't do either. Then you have to do some other work. But because e to the x is always positive, that means that we're okay to divide and cancel and make 1 in the numerator. Okay. Wonderful. So that means that dy over dx is equal to 1 over square root. Now e to the x to the 2 is e to the 2x. You can multiply your powers. Just a little reminder of how that works. If you take a to the x to the y, that's a to the x times y. It's a property of exponentials. So I'm just multiplying x times 2, so that's 2x, take away 1. And there we go. This is the slope of the tangent at all points in the domain of the function, right, at all x values. Okay, but that's not really what I want. I don't want the derivative everywhere. What I want is the derivative at my point. So that'll be step 3. I'm going to find the slope of the tangent. So find m tangent, which is dy dx at x1, y1, right, at the particular point that I'm looking at. Okay, so that means that the slope of the tangent line is going to be equal to 1 divided by, and then my x1 was natural log of 2. So this is going to be square root e to the 2. Instead of x, I'm going to write what x1 was for me, which was the natural log of 2. Minus 1. Now I need to do just a little bit of algebra work because they asked for this exactly. So just remember the power property of logarithms. So the power property of logarithms says that if you have, a times the natural log of b, then that's equal to the natural log of b to the a. That you can bring the power up in front. Okay, so what does that do? Well, it means I'm going to be able to take this 2 and pull it up and write this as 1 over square root e to the natural log of 2 squared minus 1. Okay, but that's 1 over square root e to the natural log of 4, take away 1. And then remember, yet again, e and natural log are inverses of each other, right? E to the x and natural log of x are inverses. So they're going to unravel each other and just leave 4. So this is equal to 1 over the square root of 4 take away 1. In other words, 1 over the square root of 3. There's your slope right here. There's your slope of your tangent line. All right, so that required some algebra a bit to know that because we had to do this exactly. But let's put the pieces together. We were given x1 right here. We figured out y1 in step 1. We figured out the derivative so that we could find the slope right here. And in step 4, we're actually going to write the equation of the line. Okay, so that would be y minus pi over 3, because that's my y1, equals 1 over the square root of 3 times x minus the natural log of 2. It is a little bit difficult in terms of the algebra, but the process is the same process we've used multiple times to find the equation of a tangent line. One thing to remember is that we only had to do step 1 because there was no y1 given. I had to do all this work. If there's a y1 given over here, then I can skip step 1 and jump right into taking the derivative down here. And then, of course, it helps to know all of our exponentials and logarithm properties that we've learned along the way, as well as trigonometry.